photonic integrated circuits for AI. Why, when, and where will that actually take place, right? So photonic integrated circuits also, I mean, normally in the Netherlands we talk about photonics. Quite often we mean integrated photonics. And a more colloquial term is optical chips, right? Just to get a little bit into the mood, I saw this last week going quite viral on the social media. New Chinese optical quantum chip allegedly 1,000 times faster than the NVIDIA chips, right? So that caught the attention of a lot of people. I think there's a nice context. It's completely off, it's not true. And actually I'm not blaming the Chinese press officers here because apparently there were translation issues. But it's not a quantum chip. And that is more nuanced. We have to be very careful how we assess these things. I mean, it came back this morning already in the discussion, the Q&A. We have to compare apples with apples and not with oranges. But that sets a little bit of a context, right? But let's first start by saying, because I see a new crowd, I think some of the people here, they have seen my slides in the past, or some of them. It still is good to explain a little bit what do we mean by photonic integrated circuits, optical chips. And in general, what we mean by that is to say, okay, let's take optical functionalities, lasers, LEDs, so sources, photodetectors, modulators, and all kinds of passives, waveguides, filters, splitters, combiners, prisms, all these kinds of components that you normally see on an optical bench, for example, in the physics labs or the chemistry labs, right? We try to put that all in a circuit, so all interconnected, on a piece of semiconductor. So basically a few square millimeters, right? That is what photonic integration is. What can you do with it? Or why would you want to do this? Well, there are actually quite some good reasons for that. And especially the people from the electronic side, they might recognize a few of those reasons. First of all, increased performance. Things become smaller, and because they become smaller and because they're fully integrated, it becomes more stable. If things get smaller, they're typically faster, so they have higher bandwidth, right? And what's very important, if you integrate your photonics, your whole system on a chip, that means all the electronics that you need to actually drive it and to sense and to control and to etc. All of that you can design far more energy efficiently. Actually, when we talk about the field of datacom and optical communications, systems do not gain by the photonics, they gain by more efficient electronics. So that synergy is very important. Secondly, swap, size, weight and power consumption. Very important, we make things smaller, that means they can go into handhelds, they can go into drones, they can go into aerospace, right? Maybe even implantables in the future. They are more lightweight and, of course, very important, more energy efficient. Finally, decreased cost. Same as always with chips, right? The first one is very expensive, but if you get a decent amount of volume, things become increasingly cheap. Those are important drivers. I always use the picture on the right hand side here. It basically shows how all of these fiber pigtailed components, so individually packaged lasers, 10 photodetectors, 10 modulators, all individually packaged, connected with a fiber, how they can be replaced by only one chip. And I especially like the picture because it's almost 20 years old. And that's important to notice. This is not a new technology. This technology has been powering our communications, our internet, since at least 25 years or something. A little bit more in detail for the more technically minded. What does it look like? What does such a chip look like? Well, actually there are multiple technologies. Christian already showed in the previous presentation that you have silicon. I will come back to that. This is an indium phosphide based chip, a compound semiconductor, indium phosphide, different material, but it's the material of choice to make lasers. So with semiconductor compatible processes, etching, deposition, those kind of lithography, we make these chips and we can integrate on these chips lasers, here on the left hand side, modulators, photodetectors, waveguides, and we can interconnect them all in plane, in a planar way, so that they all work together as a circuit. Only in one process. And for example, companies here in Eindhoven like Smart Photonics and the new, to be newly built fab of TNO, they will focus on this kind of technology, just like we in TU Eindhoven. Keep an eye on there. So, what can we do with this technology? You can approach it a little bit like in electronics, right? If you go to, if you are working at TSMC, you might not know what the NVIDIAs of this world are doing. Okay, you can watch the news, but you might not see it in the fab. You just have a process to make the smallest and most energy efficient possible transistors. Well, what we can think about in photonics, let's conceptualize a little bit. We have sources, we have modulators, we have photodetectors. What can we build from that? Let's leave it to the creativity of the designers. Let's decouple fab and design. And we have done this in the European network, joint European platform for photonic integrated circuits called YEPICS. We have pioneered 20 years ago so-called multi-project wafer runs. So basically we run the process, others do the design. Over the last 20 years we have served over 1,000 designs, and then you just let creativity go wild. By academic researchers, by startups, by multinationals, even ASML is playing there, right? In all kind of fields. Of course, telecom and datacom, switches for networks, transceivers, that kind of stuff. Microwave and terahertz photonics, but also completely different fields. Biomedical sensors, for example, for OCT, optical coherence tomography. Maybe fiber optic sensors to put in bridges in the wings of an airplane, for example. And of course, very popular nowadays, all kinds of quantum communications, which can be done with these kind of existing technologies. So the fabrication infrastructure is there. A very small word on this YEPICS organization. It's a European organization, and I want to highlight it because you can actually knock on their door and they can help you in 3 ways. As I said, for already 20 years we have been coordinating multi-project wafer runs, which is basically the easiest way to get into the field and to start doing your proof of concept and prototyping. Secondly, we have been running and are very much involved in the European pilot lines for photonics. So there's piloting activities, and again, the YEPICS can be a gate to that. And thirdly, knowledge. We do trainings, we do courses, every year a 2-week course, every year a 2-day course for professionals, for people that are beyond the master level. So lifelong learning kind of efforts. So it's yepics.eu if you are interested in that. And only one slide, just to highlight a little bit the technology side of the previous talk. We do not have to do this in indium phosphide alone. We can also do this in silicon. We will lack the laser. There's no laser in silicon. But we can make waveguides in silicon. We can make modulators in silicon. And if we add germanium, we can even make photodetectors in silicon. And why does that matter? That means that in a silicon fab, TSMC, Global Foundries, right? You can make photonic integrated circuits with all the maturity that comes along with it, and even with the design tools that come along with it. So this is the what. This is what is a photonic integrated circuit. So I hope you have a little bit of a flavor what it sort of is. Why did Hans actually invite me to be here, right? I think it's important to realize, okay, where are the issues where it could play a role? And I'm repeating a little bit what we have been discussing over the morning and what we just have been discussing. Where are the bottlenecks? Well, the bottlenecks are, if we look at computing power, normally a factor of 2 every 2 years scaling, the demand for it goes up with a higher slope than that. We have been discussing that quite a lot this morning. What does it mean? Probably you need to have new computing paradigms. So let's keep that in mind. We might need new computing paradigms. A second thing that's very important is just the backbone a little bit. So you can have a very nice chip, a very nice CPU or GPU, but it needs to communicate with the outside world. And whereas with Moore's law, the transistors scale very nicely, the interconnects and the connections to the memory bandwidth does not necessarily do so. Bandwidth is limited, energy efficiency of that is limited, latency gets limited. So all of these things call for a solution. There are various potential solutions. People have been talking already about in-memory computing. But you can of course also think about just new ways of actually interconnecting your chips, or even interconnecting cores on a chip, for example. So that's the background. Why would we be interested in photonics? Because potentially they can solve some of these problems. So where do we think photonics can actually solve some of these problems? Well, the first one is a little bit of a no-brainer, because we already use photonics. We use photonics to connect already since 30, 40 years continents, countries, cities, right? Eventually data centers, also going to the home. 25 years ago I had fiber to the home connection in our student housing, right? And nowadays the photonics gets closer and closer to within the data centers, within the racks, within the servers, even getting closer to the chips nowadays. So that's the trend. What is actually, if you formalize that a little bit more, what is the trend? So it's a bit of an old picture. It's a picture by Mellanox, one of the companies that was bought by NVIDIA. It's a little bit of a technical picture, but what the picture shows you here is that vertically you see data rate. So the bandwidth that is required somewhere could be telecom, Amsterdam to New York. It could also be the CPU to the memory, so it's arbitrary. And horizontally here you see the link length. And what this picture shows, zoom out a little bit, you can see these diagonal lines. What it shows is that if you go to a shorter link length, the case for replacing copper, coaxial cables, copper lines with photonics becomes more favorable. That's why you have these diagonal lines. So the shorter the link, the more it becomes, so diagonal lines come into play later. The shorter the link, the more copper is favorable, and the longer the link, the better you go to photonics. That's because you have an offset in electronic, photonic, and vice versa conversion. So why are the lines diagonal here? That is also because the more data rate you need to have, the more photonics becomes favorable. A coaxial cable is of course limited, copper is limited in bandwidth, optical fibers are limited to hundreds of terahertz bandwidth, so no problem there. So you have this trade-off between the two. And what you now see is for a given link length, throughout the time you will go vertically on this line, and you will see an evolution from copper towards maybe in between cheap optics, VCSELs, multimode fiber, to eventually integrated photonics. So, and eventually that will happen for even the shortest link lengths, because it's more energy efficient. It has more bandwidth, density. How does the field play on that? Well, here's an example of global foundries. So what we see is for shorter and shorter link lengths that things come together. So global foundries is anticipating on that by actually having a process that has both transistors and photonics in there, enabling that you can have these semicon grade technologies to eventually merge, okay, maybe not monolithically with the processor, that can be done through chiplets, right? But at least having the drivers, having the control monolithically integrated with the photonics. In one process, in a very mature process, I think it's, as you can see here, 45 nanometer process. So it's not the state of the art, but you don't need to have that. And this is part of a wider paradigm of heterogeneous integration. What we are slowly looking for is the closer and closer integration of electronics, of photonics, of also different kinds of electronics, obviously. And we can think about a lot of ways. That's actually our research field, to figure out how that goes together. That can be done with chiplets, that can be done with microtransfer printing, that can be done with wafer bonding, die bonding. There's a whole zoo of options out there that can be considered for this kind of approach. Flip chipping, of course, very important one. So that is out there, and people are actively researching what is now the best option for that going forward. It's not an academic effort. Well, first of all, because especially the assembly here, that is pretty mature anyway. It's also pretty expensive, and it's the playing field now of some of the big players. I mean, Intel was maybe one of the first to actually really, as a CMOS company, as a semicon company, who really went into the photonics. They presented, I think 2 years ago on the OFC, this 4 terabit per second, what they call optical compute interconnect. You see sort of a 2.5D, 3D integration kind of approach with the CPU or GPU, with some kind of interposer, and then photonics with the electronics integrated next to it. So that you can actually bring the optical fiber all the way to your package, and you only have the high bandwidth copper here in between, right? So you really minimize the distance your signal has to go to copper. This morning we already had a presentation by NVIDIA, right? So this is just a picture from them. Last year they presented this, or half a year ago, what they call the X Photonics, Spectrum X Photonics, co-packaged optics. So it's a prototype, I don't think it's a product yet, so they actually play around with that, right? For a total bandwidth here of 100 to 400 terabits per second, right? Going in and around this whole thing, with all kind of co-packaged little transceivers made in this case, silicon photonics. I think it's silicon photonics. So a lot of these things happen. By the way, the disclaimer, bottom left there, NVIDIA also stated, you know, copper still works, right? So we can do this, but we are not implementing it yet. We still squeeze out the copper as much as possible, right? So the little interconnect lines. So that is about interconnects. I'm not an expert in computing, in neuromorphic computing and optical computing, but I want to at least give you a pointer towards that direction, because this is a meeting where we also talk about that. Yes, you can also use photonics for computing. Until now I've been talking about using photonics for communications, right? And even for communications inside computers, right? But this is really, can you also do computing with it? This is work in 2017 from MIT, right? They did some kind of neuromorphic computing. Voice recognition or vowel recognition, so you see on the left-hand side, I had speaking, and you have the vowel recognition on the right-hand side. It's an artificial neural network, so conceptually top left. You can make something similar with photonic networks. So the first networks here, they were mostly linear networks. So basically, consider your linear algebra, matrix operations, right? The non-linear elements, they were off-chip, so there was still a limitation, but you can do that. And it worked, right? So they actually made a chip, as you can see over here. Spin-off companies came out of it, Light Matter, Light Intelligence, both still exist. So conceptually it works. However, there are a little bit of a caveats here. And that also refers back to the first slide I was actually showing you about this claim by Shanghai University about the NVIDIA, 1,000 times faster. Yes, maybe on that matrix operation part they are faster, but typically you have to read the literature very carefully. Quite often electronics are not included. If you want to talk about photonics, you need to talk about transimpedance amplifier, digital analog conversion, analog digital conversion, etc. Right? Signal processing. It's typically out of the equation. Electro-optic, optoelectronic conversion, typically out of the equation. So any energy metric you see, you have to take with a grain of salt. We use a lot of gold, by the way. Which is a problem because it's sky high, so we have clean room issues, but it's a different story. And there are technical challenges to solve. right? There are still the phase tuning here to make that low energy consumption is still a problem a little bit. And of course, in the neuromorphic part, photonics is based on bosons, and all the physicists here know that photons do not really interact very well. That means that, okay, we have optical non-linearities, but to do it at low energy, that's really a challenge. So, the last two slides are a little bit speculative, but you know, we end with a drink afterwards and we have a Q&A, so I think we have something to talk about. When will this happen? Huh? So, a little bit of context here first. For me, when I talk about timelines, in this field, in the field of what we call exponential technologies, memory, compute, communications, all these technologies that tend to grow by a factor of 2 every 2 years, all these technologies that are extremely mature. For me, I always have the sort of guideline for myself. 10x growth is industrial R&D, right? And that will happen in 5 to 10 years from now. 100x growth is engineering science. So the electrical engineers, the mechanical engineers, you know, those kind of people have to do their job. It might be RTO, it might be at universities, right? Up to 20 years away. And then of course the 1,000 times growth, that's where the natural science, the material science comes into play, right? Very fundamental new things. Yeah, that is typically 20 plus years ago, but it's also a little bit of a crystal ball, right? It's a long way to go. So that's my context that I typically apply to, you know, my vision on when will things happen. So the two things that I discussed now, optical interconnects for supercomputers, for AI, to connect chips, and optical processors. Well, when we go to the optical interconnects, specifically going to the packages, co-packaged optics, people have been talking about that a lot, and it's always, you know, it's always next on the horizon. But I think the momentum is now there that we can start saying it's less than 5 years away, right? It always goes, especially for a professor, it always goes slower than you would want. But I mean, this is really getting there. If you see the momentum that is in there. When we talk about processors, I'm not negative, by the way. This is just me being realistic, but I think that's at least 10 years away. Photonics-based processors, so photonics-based computing. That is also, if you look at the industry a little bit, the industry that has started this, it's currently struggling. They are moving away from it, or they go bankrupt. So that's unfortunate, but it's what's happening at the moment. So the underlying technologies are there, the underlying potential is there, but I think we need to step up a little bit to make that happen. And that's my last slide here, or my second last slide, sorry. Because of second slide, the previous one was when. I'm 100% sure photonics will happen, but we want to make it happen in Europe and in the Netherlands. So what are our bottlenecks, in my opinion? We have a few bottlenecks, a few problems. We have all the ingredients, but we lack the recipe. We don't really know yet how to bring it together. That's why the little alarm bell here. We need 3 mindset changes, so to say, in my opinion. First of all, integrate photonics. It needs to be considered as part of a semicon roadmap. We have the same kind of manufacturing, we have the same kind of design tools, EDA, electronic design automation, EPDA, and we need the similar kind of talent. We need people with both skills. That goes synergetically together, yes? Secondly, we need quantified roadmaps. We are working completely independent of each other, and I, as a technology enabler, would not know what I have to develop to actually make all of this happen. And that's a problem because we are really running the pilot lines. So there's no technology available unless people tell us what we should do. And finally, heterogeneous integration. That is something that is out there, it's mature, but in a large way, especially academia, is very disconnected. Yes, IMEC can be on top of it, but IMEC is rich and IMEC is very well networked, but also academia has to start getting on top of it. And as a last slide, so our initiative, but we only started this one 2 months ago, our initiative at TU Eindhoven to actually get on top of this is what we call our Casimir Institute. We founded it 2 months ago, the Casimir Institute for Future Chips and High-Tech Systems. And we think the future is not only looking at chip, but also towards the potentially new materials that can enable those chips, but also towards all this tooling, all this equipment that can actually enable this whole heterogeneous integration that's necessary. And with that, I would like to end my talk. That's my LinkedIn QR code, so always happy to connect. Thank you for the attention.